So I'm Dr. Jithin Jagannath. I'm the Chief Scientist of Technology at ANDRO. I also play the role of founding director of our Marconi-Rosenblatt AI ML lab. So as the name suggests, right, Marconi was a pioneer for wireless communication, and Rosenblatt was a pioneer for machine learning. Primarily, we focus on R&D efforts for DoD and other federal entities. And our area of research is wireless communication. And I've also been able to expand that to applied machine learning for ANDRO. Okay, so biggest advances in spectrum technology. So, the things that pop into my head immediately are spectrum sharing from a cellular point of view. But the community is well aware of that. So let me take a couple of different directions with this one. So recently, actually yesterday, we had an interesting milestone in one of our projects. This was a Rapid Innovation Fund project for the Army. So the goal there was to look at distributed radio networks. So you can think about a battalion that goes with handheld radios, and they have predetermined frequencies that they're allowed to use, but you don't choose the channel on top, right? So the goal there is, can machine learning and deep reinforcement learning can be deployed on the radios itself, where these decisions can be made on the fly. So what we did is we created a congested and contested environment where there are friendlies. There were 3 jammers which had different kind of waveforms. You can think about chirp waveforms, you can think about frequency hopping waveforms, and they also randomly chose their center frequency to actually use and transmit that. So 2 of our concern is, can this be done in real time? And to test that out, we said, okay, we're going to transmit video as our data. So video, as you can imagine, there's latencies between frames that has to be kept. So the decision-making cannot be really slow. So slow decision-makings will cause jitters and lags in the video. So that's why we chose video as a transmission. And the other aspect was, we cannot rely on cloud deployment. We have to deploy the machine learning on the radios itself. And for this particular project, we used Deep Wave Digital's AT SDRs, which had an embedded GPU on it. But interestingly enough, it was a great milestone for us. We were able to show video transmission in congested environment using LPI, LPD waveforms. And these machine learning models were able to choose spectrum, choose frequencies that were not jammed, were able to choose power levels. The power levels are important because I have to make sure that my transmission or data goes through, but I have to also care about the neighboring nodes that might be trying to do the same. So, and this is being done in a distributed manner where there's no centralized entity telling you to choose this frequency and this power level. Each radios are choosing that or learning to choose that using a deep reinforcement learning engine. And that was pretty interesting for us because that answers 2 of the question. It can be done in real time and it can be deployed on the radio itself. Now you can see the implications of this for larger 5G, beyond 5G solutions, where similar techniques and resource management is happening. And this was a great Rapid Innovation Fund milestone for us, which we demonstrated to our Army. The second aspect that maybe is not looked at that keenly is the security when you start thinking about spectrum sharing. So we had a project, that DHS CIBER project, where they wanted us to look at what happens when you try to share spectrum, say between Wi-Fi 6 and 5G in the unlicensed band. So if you think about it, it's an unlicensed band. It's not as well regulated as licensed band. There could be entities that set up transmitters, try to mimic base stations, and in a tactical environment that are security sensitive, these things become really critical. So we looked at and we devised a solution where the security aspect takes place right at the top, right at the bottom in a way, because at the spectrum level, even before the data or the packets get into the network, we only allow authorized users to access spectrum, even in a spectrum sharing environment. And that's significantly overlooked at this point because every network takes care of itself. But what about the coexisting network? So that was an interesting study. And we have patents on these technologies. And even after allowing the user authenticatedly within the networks, we have a zero trust engine which sits within this 5G framework and tries to determine, is somebody behaving oddly? What's the trust level of these entities? And that, again, is going to become a key entity given the wide use of IoT devices. So you have hundreds and thousands and billions of devices. How do you monitor all of them? Once you allow them, do you trust them completely? Which may not be true for tactical applications because they could be infiltrated, tampered with after authentication. So you want a mechanism to continuously monitor the trust level. So with zero trust, security from a spectrum sharing point of view is going to become important. And we have couple of interesting projects and solutions that we have developed for the same. So those are the two big advances that I can think about from a spectrum technologies. Challenges on spectrum sharing technologies are also drivers and opportunities for us. So immediately when I think about challenges, I can think about latency. How much time would I need to make this decision? I can think about, can I deploy our solution on the radios itself as opposed to a centralized unit? And we already just in the previous question, we talked about some of that is possible. We have overcome some of those challenges. Now, let me put a different perspective to the spectrum share. So the first information or first quantity of information you need before you start sharing spectrum is who is accessing the spectrum? What are these entities that are, you see an energy in your spectrum? How do you know whether it's a legitimate user? How do you know who is using it? So we call this part of spectrum sharing as signal intelligence. The more intelligence, more comprehensive intelligence you have, you can make the spectrum decision. And this is exactly what we're doing. Like in the project that I talked about, first you look at the spectrum and learn about the spectrum, and then the reinforcement learning engine tweaks its parameters to choose what frequencies and what parameters to apply to that particular radio. So signal intelligence is pretty keen, and I think so that's going to be an interesting area to look at. And we have 3 different projects that is exploring that. The most common one anybody can think about is modulation classification, knowing whether it's an LTE signal versus a Wi-Fi signal. So those are standard classifications, but can that be done so efficiently that now you don't need a large deep GPU machine to deploy this, but you can deploy it on the radios, on FPGAs. So, hardware-based acceleration for these spectrum sensing technologies or signal intelligence technology is going to become key. And it's not enough to know the modulation, right? Can a single model tell you what modulation it is, what kind of signal it is, and go a step further, that is RF fingerprinting, actually tell you what radio is? For example, you could use that to differentiate between the radios that the fingerprint of your friendlies versus an foe who might be trying to mimic your own signal that is being transmitted. So RF fingerprinting might help you classify that. Another aspect of RF fingerprinting is if you keep a database, if you see an unauthorized user and you start seeing patterns, you can start recognizing there's one unauthorized user versus 2. Are you seeing the same person again and again? But the question is, can all this be done in a single model, in a single solution that can be deployed at the edge or even on the radios itself that are currently out there on the FPGA? And we have an Army project that's looking at this, and a SOCOM project that's looking at the RF fingerprinting aspect of the solution. And that's going to become very interesting for us. Going a step further, we just have been awarded another Army project that hasn't started yet, but it asks the next logical question. So you know all this information about the spectrum usage that's going to help you manage spectrum even better or take decisions. But now, can you start predicting your unknown users, right? So you see a spectrum behavior, you see it over minutes, seconds, hours, days, but now can you start predicting it both from how it's going to move in the actual domain, but also how it's going to move within the spectrum? So a complete comprehensive signal intelligence tool that powers next generation of signal processors, next generation of spectrum sharing is going to be key. And that's still a challenging aspect because, if it's machine learning solution, there's lack of data sets while people are making strides and we have some of our data sets, but still it is an area that we need more work in, and knowing more of the spectrum, knowing it in real time, being able to predict it is going to make some of our spectrum sharing technologies even more robust. These are just one of the challenges. Like I said, I could talk about the spectrum sharing challenges for next half an hour with the traditional challenges associated with it. But I thought I'll give an idea of what needs to be done, maybe even before spectrum sharing, to give the spectrum sharing engine even more information from a SIGINT point of view. So yeah, it's a very interesting area. For us, R&D and prototyping are equally important. And I've already talked about multiple R&D projects. So what we do is we use these. So some of the concept that we come up with, it's high risk, high reward concept. So we want to rule out some of the hypotheses and then, change things as we go and make sure that we reduce the risk as we keep developing. But what happens usually is after SIBR phase 1 or phase 2, we look at ways to mature this into a product, into a solution, and a prototype. And that's where NSC and other efforts come into play. A great example would be there was an NSF challenge that we took part in. The idea was to design energy-aware, rapid, low-cost routing for disaster scenarios. When the traditional networks are down, how do you communicate? So interestingly enough, 1 year or 2 years later, Army came out with a requirement where they wanted to deploy similar energy-aware solutions for their test and evaluation ranges. And that was a rapid innovation fund project that we won. We actually took the idea from R&D to actual product called Spearlink. So this product, what it did is it's ruggedized, it can deploy it in harsh conditions, it does spectrum sharing like we just talked about, it is able to change spectrum when it's needed to. It's energy aware. It means it just doesn't say, for example, choose the shortest path. Rather, it chooses if there is a node that has more energy or is plugged in, it would prefer that node so that the overall network stays up and running during the entire test and evaluation exercise. So it was almost like a telemetry collection network, but it's ad hoc, self-healing, self-forming. Even if a node comes out or goes in, it really doesn't affect the overall network. It finds its route on its own. And this product actually came from an idea. It's now an actual product that is available for purchase, right? So both these aspects are key for us. And what we do is we start with some innovative R&D, rule out things that do not work, focus on things that do, tweak them so that they can become into more mature product and solutions. And that's been part of our business model for the last 3 years. Yeah, we covered some of the interesting projects that we have been working on. There's actually one that I can mention. So like I said, in our lab, ANDRO's Marconi-Rosenblatt lab, we look at wireless, applied AI ML, but there's also other applied AI ML to other domains like computer vision. So there's an interesting project that I'm working on that's a Navy cyber phase 2. So the whole goal there is to look at UAVs, autonomy for small UAVs, where it can avoid collisions. If the mission objectives changes, it can take actions on its own with a human on the loop. So the idea there is if there is a UAV that can avoid collisions, can follow entities, now this could become an UAV-assisted RAN technology, right? So you can think about a mission where it's a remote area, there's no communication infrastructure. Now this UAV that is doing computer vision-based autonomy, it can fly, it can follow, say, a platoon or a battalion. So what happens is it becomes a joint optimization problem where now UAV follows, but also takes care of maintaining the link. So it kind of optimizes both link robustness and its own collision avoidance and following. You shouldn't be using too much energy because obviously batteries are a big concern on smaller UAVs. But that's how it's a little different from some of the other projects that are core AI ML for RF and wireless communication. This is more of a computer vision, UAV autonomy control kind of a solution. But in future, or even there's already a lot of work being done in other domain, but I see this might combine to become maybe an critical communication delivery UAV that provides 5G communication or other communication sources for remote deployment for a short, fast mission, but where communication might be critical, and this might be the source of your communication. So that's one other project that I can think about that we haven't touched upon. But overall, our mission has been to look at advanced wireless communication, LPI, LPD, the part of the solution that I just talked about the Army RIF, which we demonstrated. The physical layer itself is LPI, LPD jammer resilient, so it can actually transmit over jammer. But we added the upper layer AI ML engine or deep reinforcement learning engine to say, okay, if the jammer is really close to you, there's no way to communicate over jammer. Can it learn to avoid it and also coexist with the threat? So these have been our key areas of interest, and we're looking at ways to both develop new technologies, mature it, and as part of all these efforts, we have about 11, 12 patents that are at different stages. Some of them have been approved, some of them pending, and those are our ways to mature these technologies into actual products that will be useful for the end user, both DoD and commercial realm. So that's a good overview of what we have been doing.